Well, I hope we're doing well. As promised, some implicit differentiation videos to help us get a firmer understanding of this. As we said in class, thus far we've been taking the derivative of equations that are defined explicitly. Until such time as you encounter ones that are implicit, you don't have a specific name for them. You just think of these equations as equations, right? Because that's just the way things are. That's the way they've always been. And so if we can actually isolate the output variable and state it as output equal to some expression of the input variable, this is what is known as an explicit equation, okay? Whether it be f or whether it be y. In this case, y is stated in terms of x, and in this case, f is stated in terms of t. Notice that there are no y's over here on the right-hand side. It is pure x, or constant, of course. Same thing here with f. There are no output variables here blended in. It is all in terms of the input variable. These are explicit equations. Now, when you finally get to something like conic sections or whatever, you realize that not all equations are stated explicitly. Oftentimes, they're implicit. And that doesn't make them less meaningful for them to be stated implicitly, or for, in the sake of conic sections, for them not to be functions. It simply means that they're just stated differently. Okay, let me zoom in just a smidge. So what we have here is we have, this one of course is a circle, and if you want to, you can go ahead and graph that on your own to determine. I'm not really worried about the graph right now. I'm worried about the fact that y cannot be isolated here. Okay, y cannot be isolated such that it can be stated as a equation y equals some expression of x. And because y and x are sort of embedded together within the equation, we just leave it like that, and we deal with it like that. And it takes a little getting used to, but it's not really that big of a deal. Okay, now when we have those equations that are defined implicitly, we need to apply calculus to them as implicit equations. And that's what this whole section is about. It's about how to apply the derivative or differentiation to an implicit equation, and we have to wait until after we do the chain rule because it's related to the chain rule, right? So if we have the equation y is equal to, f of x, some function of x squared, we know that when we take the derivative, it's 2f of x f prime. Now we have to have this f prime right here because f of x is not x. It is some expression in terms of x, or it has some relationship to x, but it is not x. And therefore, we have to basically recognize the f of x as the stuff, right? Remember, this is stuff squared, and what's the derivative of stuff squared? 2 times stuff times the derivative of stuff, okay? Now, the same sort of thing has to happen when you're dealing with implicit equations and the derivatives of them, okay? And like it says here, there's an implied relationship to x that needs to be recognized here in the f prime. And so we're going to do roughly the same thing when we're dealing with an implicit equation. So let's go back to the equation to the circle that we were discussing just a few moments ago. Notice that x squared and y squared. Well, we could solve for y, but we would wind up getting 2 equations, right? The first equation would be the top half of the circle, and the negative would be the bottom half of the circle. But I don't want to deal with it as breaking this up into 2 separate functions and 2 separate equations. I just want to deal with the circle as the circle in one equation, okay? And so when we differentiate it with respect to x, we can do it to both sides. Remember, differentiation is an operation, so we can, what we do to one side, we have to do to the other. And of course, by rules of differentiation, we remember that we can split it up term by term on the left-hand side. Now, on the right-hand side, it's the derivative of a constant, and a constant changes not at all, hence why its derivative is always 0. Now, When we get to the derivative of that first term, the x squared, well, that's easy enough. I mean, notice that the variable the variable which I'm differentiating with respect to matches that variable. So the derivative with respect to x of x squared, well, that's just 2x. That's just the plain old power rule. We learned that a while back. Now, when we get to y squared, that's a little bit more difficult because y squared kind of acts like f of x squared, right? It's not x. That variable that I'm differentiating with respect to does not match that variable, but I know that y has an implied relationship to x. And since it has an implied relationship to x, it needs to behave just like the f of x in our earlier chain rule explanation, right? That's stuff squared. And therefore it needs to become 2 times stuff times the derivative of stuff. Or more simply, just 2y, y prime. Okay? And so basically, when it comes down to just, I mean, obviously I want you to understand why, but, obviously, the why can sort of awaken within us gradually. I do want you to understand the mechanics too. The method is, if the variables match, you don't need a y prime or anything like that. If the variables don't match, you need to do it sort of chain rule style, and you wind up with 2y, y prime. Okay? And so we differentiate the first term, we get 2x. Differentiate the second term, we get 2y, y prime. And of course, when we solve for y prime, we're going to get negative x over y. And that actually is our derivative. Okay? Let's go ahead and do some examples, and we'll sort of talk through them in much the same way. Okay? So we have e to the y is equal to tangent x. Now, I could solve for y, but let's just, on some of these where you could solve for y, let's just pretend that we can't, okay? Because these are sort of training wheel questions, and so we're going to treat them as such, and then we'll get to the more difficult ones. But since this is not e to the x, since I'm differentiating with respect to x, this is e to the stuff. And the derivative of e to the stuff is e to the stuff times the derivative of stuff. Okay, and over here, now this variable is going to match. Since I'm getting dy dx, I'm differentiating with respect to x, the variables match, and I'm left with secant squared x. Now I simply need to solve for y prime, and I'm going to get secant squared x over e to the y. Something similar, happens here. Basically, I need to remember, first of all, that this right here is a product, so I can't get so bogged down in trying to get the implicit part right and make sure that I, designate a y prime when I'm differentiating that factor right there, that I forget the product rule as well, okay? So remember, we have the derivative of the first times the second plus the second times the derivative of the first. So that just becomes y prime. And then, of course, like I said in class, you'll be so busy making sure you get this right that you'll accidentally, and this is a common mistake, you'll accidentally fail to differentiate the constant and come up with 0. But this one becomes x cubed y prime is equal to negative 3x squared y, or y prime is equal to negative 3x squared y over x cubed, or negative 3y over x, right? If we want to simplify and reduce. Now, this one, of course, we could have gotten y is equal to 8x to the negative 3, okay? And if we wanted to differentiate with respect to it as an explicit equation, then, y prime is equal to negative 24x to the negative 4. And you're like, well, that doesn't bear any resemblance to that. Well, actually, yeah, it kind of does. Because remember that is 8 over x cubed. And if you were to take that and actually substitute it right in there for that y, you would get this right here. Okay? Now, of course, you're probably thinking, well, if you can then do it that way and get it in terms of a single variable, then why in the world would you get it in terms of two variables and do it implicitly? Well, like I said, these are training wheel questions, and so we're basically going to go through these, and then we're going to take the training wheels off and do some, because like anything else, there are problems that have to be done implicitly, and then there are problems that simply can be done implicitly. So we're going to go through a little bit of both, but all of this is just an excuse to work on these strategies, right? Okay, well, I don't like this. Let's change the form to that, okay? Now I can use the power rule, and when I differentiate x to the negative 1, when I'm getting d dx, right, if I'm differentiating with respect to x, this becomes negative x to the negative 2. This becomes negative y to the negative 2. Well, when you bring down that negative, it's going to cancel out with that negative and become plus y to the negative 2. But notice I'm differentiating with respect to x. This does not match, and therefore you need to tack on a y prime. And of course, the derivative of a constant is always a constant. So you have y to the negative 2 times y prime is equal to x to the negative 2. And y prime is equal to x to the negative 2 over y to the negative 2. Oh, wait, let's go ahead and put both of those where they belong, as insofar as the negative exponents are telling us to swap them. And that is my derivative. Let's go ahead and do this one, okay? The derivative of this first one is simple enough. It's going to, with respect to x, the derivative of x squared is 2x. The derivative of y squared is 2y, y prime. And the derivative of xy, remember that we have to do the product rule. Okay, so it's the first times the derivative of the second plus the derivative of the first times the second. And then, of course, the derivative of that constant is 0. Be careful to distribute the negative across, and we're going to get 2x. Let's go ahead and just rewrite it without the brackets and the braces before we start grouping things together. Okay, I notice that this term and this term have y prime. The other two don't. So we're going to send the other two over to the other side. Let's go ahead and negative 2y prime, negative x y prime is equal to negative 2x plus y. Well, I don't like the negatives, so let's go ahead and multiply through by a negative. Factor the y prime out. And my y prime is going to be 2x minus y over 2y plus x. Ta-da! Okay. Now, let's go ahead and do one that's, a little bit nastier. Okay, have a few exponentials in there. Now, we're going to need the product rule here, and we're going to need the product rule here. Okay, so the derivative of the first, actually let's just do the first and the derivative of the second. Now, the derivative of cosine x, we know this, it's just negative sine x. Okay, that's supposed to be e to the y, sorry. Plus, the derivative of e to the stuff is e to the stuff times the derivative of stuff, so we have our y prime, and then cosine x. Now that right there is the derivative of that first product, that first term. Let's do the second one. E to the negative x times cosine y times y prime, right? Because that's sine of stuff, and the derivative of sine of stuff is cosine stuff times the derivative of stuff, plus negative e to the negative x times sine y. And of course, remembering that the derivative of a constant is 0. I have a y prime here. I have a y prime here. The other two need to go to the other side. And so I have e to the y cosine x times y prime plus e to the negative x cosine y times y prime is equal to, well, both of these wind up being negative, so when we push them to the other side, they wind up being positive. I get e to the y sine x plus e to the negative x sine y. Let's go ahead and pull out our y prime. And once we pulled out the y prime as our GCF, we then, of course, treat this like it's the coefficient of y prime. We divide through both sides by it, and we wind up getting this nastiness right here. And that's it right there. And as nasty as that is, unfortunately, there seems to be no way, at least no visible way right now, to get rid of it. Okay. I mean, I guess you could multiply both the numerator and denominator by e to the x in order to get rid of the implied complex fraction. Oh, the complex fraction that's implied by these negative x's. And if you did that, basically, you would, you would just get, it would basically, when you distributed it to both terms, it would eliminate these and would simply become something like this. But that's unnecessary. I mean, this right here is sufficient. And of course, as always, I mean, when you're trying to figure out how to simplify or what final form a derivative should be in, it pretty much needs to be in whatever form is going to be most advantageous for the next thing that you're going to do with it. Okay, I'm going to go ahead and call this video finished and bring it to a close. As always, if you have any questions, please do shoot me an email. Bye.